Alrighty, so today we are talking about section 2.7, and it's all about x goes to infinity, or negative infinity. Either one is fine. Either one is what we're talking about here. And this is stuff that, or at least a lot of the section, a lot of the focus of this section is stuff that secretly you've done in pre-calculus, most likely, because the limit as x goes to plus or minus infinity of f of x describes the asymptotic behavior of f of x, specifically the horizontal asymptotes. So when in pre-calculus you were talking about rational functions and having to find horizontal asymptotes for that, you were talking about the limits as x went to positive and negative infinity. So that sort of stuff can be familiar. And I'm going to go over some quick ones that we have. First off, the limit as x goes to infinity of e to the x is equal to infinity. E to the x keeps growing without bound, right? So exponential growth is a thing, and it doesn't cap off anywhere. But the limit as x goes to negative infinity of e to the x is actually 0. If you look at a graph of e to the x, it never goes negative. It never goes down below the x-axis. So the limit as x goes to plus or minus infinity of sine of x does not exist. And same for cosine of x. Neither of those exist because as x gets bigger, sine of x and cosine of x both keep oscillating between -1 and 1, right? It never gets particularly close or closer and closer and closer to any one number. It just goes back and forth between -1 and +1 forever. So it's not ever zeroing in on any one value, right? But the main focus of this section is about rational functions. So basic power functions are pretty easy. The limit as x to the n as x goes to infinity is infinity. The limit as x goes to negative infinity of x to the n is equal to infinity if n is even, and negative infinity if n is odd. Right, which hopefully makes sense. If you have an even power, you're multiplying that number by itself an even number of times. So even if you're multiplying a very, very negative number by itself, if you're multiplying it by itself an even number of times, all those negatives cancel out, and you just wind up with a very, very big positive number. And if you're multiplying it by itself an odd number of times, all of them but one cancel out, and that last remaining one keeps things negative. So we also have the limit as x goes to infinity of x to the negative n equals 0. And the limit as x goes to negative infinity of x to the negative n is also equal to 0. So those are our basic power functions, right? And I list those out because we have a nice rule for full-on rational functions, is that the limit as x goes to either plus or minus infinity of a rational function, right, which remember looks like some polynomial divided by another polynomial, right? That can be big and complicated and confusing, but it turns out that we can pull, those leading coefficients out and just look at the limit as x goes to plus or minus infinity, and this will be the same as whatever that is, of x to the n minus m. So basically, if we have this whole big long thing, we can chop it off and just look at these two, right? Because it turns out that as x gets bigger and bigger and bigger, only x's with the highest possible power make any difference, right? And so that's why we just chop off those two leading terms and just deal with them. And we even have some ways to simplify it more, which we'll get into more with the problems. Let's leave this up here for reference for our first couple problems at least. Right. So we have the limit as x goes to negative infinity of right. Well, our rule here says that we can find the leading terms, right? So the leading term up top is this guy. The leading term over here is this guy. We can pull out the leading coefficient and then just look at the limit as x goes to negative infinity of x to the 7 minus 8. So that's going to be a negative number. So I'm going to be looking at this basic rule. And I know this is going to be 3/10 times 0. Right? So as simple as that. Let's have the limit as x goes to infinity of 2x squared plus x to the 6th minus 10 all over right. So just like we did before, we need to find the leading terms, and I've been tricky with this one in that I haven't put the polynomials in proper order, right? Leading term, if we recall, does not mean the one that comes first. It means the one with the highest power. All right, so our two leading terms are x to the 6th up top and negative 2x to the 6th down below. All right, so we get 1 over negative 2 when we pull out those leading coefficients. The limit as x goes to infinity of x to the 6 minus 6 and x to the 6 minus 6 is x to the 0, which is just 1, so we get negative 1/2. Right? And one more along those lines. I want to get all the different varieties that can come up on these basic problems. Let's do the limit as x goes to negative infinity of negative x to the 9th plus 2x to the 7th minus 12x plus 2 all over three x to the 6th plus 4x to the 5th plus 3x to the 4th minus 1. So in this case, again, we need to find the leading terms, right? So I did it in the proper order this time. So those are our two leading terms. So we want to pull out the -1 and the 3. And then we're looking at the limit as x goes to negative infinity of x to the 9 minus 6. So that's the limit as x goes to negative infinity of x cubed, right? So that means we're looking at this guy here as our basic example for it. So the n in this case is 3, right? So we're looking at n being odd. So we know this is -1/3 times negative infinity. And now I'm going to feel bad about putting this up on a public space because that's horrible. That's bad. You can't really multiply -1/3 by negative infinity. The main reason I put it there is to note that while you can't really multiply these, you do need to have this negative cancel out. Right, so you are kind of multiplying by it. The 1/3 doesn't actually change the fact that it's infinity, but the two negatives do cancel and mean that you get positive infinity. Right, so we get a negative infinity because n is 3 and therefore odd. And we get a negative because we had to pull out a -1/3. And we know that the limit as x goes to negative infinity of this guy is positive infinity. All right. So those are our basic rational functions. It turns out that we can super cheat and do this same sort of thing even when it's not quite rational. So the same trick that we worked out will serve just fine when we have roots. Right. So we still want to find the leading term. Right, so it's still these guys with the biggest power. But we have to take into account this root. So when we pull out the coefficients, we're going to have the square root of 3, not just 3. And then, whoops, I suddenly changed variables for no reason. We have the t cubed because that's just by itself under the root. But this power, we can't just leave it at 5 because it's underneath a root. So it's going to be 5/2, right? Because a root is a 1/2 power. And when you raise a power to a power, you multiply those powers. Right? So we get 1 over root 3. Limit as t goes to infinity of t to the 1/2. And so this, if we look quite at our thing, our rule was more about n, which if we're saying that n can be even or odd, we really mean integers. But as long as we're careful about where those roots exist, we can use the same basic idea, right? So the square root works just fine with positive numbers. And so it's going to work just fine over here, and we get infinity out of it. Right? Let's see. All right. So here we're going to do the same thing. We're going to find the leading terms. Right? And so this is going to have a 1 again. And we're going to have the 6th root of 7. We'll do the limit as t goes to negative infinity of 4/3 is the one up top. Right, we get the 4 and the 1/3 from the root, minus 4/6. Really, the minus is up here. Again, we get the 4 from here and the root from there. So let's get a common denominator. And then we figure out we're looking at 1 over the 6th root of 7. Limit t goes to negative infinity of t to the 4/6. Right? Yes, I could have also simplified the 4/6 to a 2/3, but regardless, it doesn't matter too much. Right? So now if we look back all the way up here, we are in a situation, right? We are in this situation where we need to know about n being even and odd, right? But if we think about why n being even or odd mattered, it's because if we multiply a negative number by itself an even number of times, it becomes positive. And if we multiply a negative number by itself an odd number of times, it becomes negative, or it stays negative, rather. So when we look at this guy here, the 4 tells us how many times we're multiplying t by itself, right? The 6 tells us that we're taking the 6th root. So this 4 is the piece that matters for being n even or odd, right? So I know that this is going to be positive infinity. All right. Let's see. One other sort of tricky bit, so that's one tricky bit, is that the even or odd, when that question comes up, depends entirely on the numerator of your power, if your power is a fraction. In a similar sort of case, or a similar kind of issue, all right, let's look at the limit as x goes to negative infinity, the square root of 3x to the 6 minus 10x all over 2x cubed plus 11x minus 1. Right, so again, we need to look at the leading terms, right? So what it seems like this should be is we take that square root of 3 divided by 2, and we say the limit as x goes to negative infinity of x to the 6 halves minus 3, right? And I'm actually going to write it a little differently just to illustrate what's going wrong here. Right, so usually we can simplify 6 halves to 3, and this just cancels out and becomes root 3 over 2. Right, so that's what it looks like should happen. But when we have fractional powers like that, we have to be really careful about what we've plugged in. Right, because it turns out that, so in a thought bubble over here, the square root of x squared, that's equal to x if x is greater than 0. It's equal to negative x if x is less than 0. Right, because the square root of x squared is always going to be a positive number, because square roots are always positive numbers, right? So this looks like it should be, right? So the square root of x to the 6th is a lot like x cubed if, right, so another one here, we can extend that. The square root of x to the 6th is equal to x cubed if x is greater than 0. It's equal to negative x cubed if x is less than 0. Right? And you can write it as either one if x is equal to 0, because it doesn't matter. But, so we have to be careful here and carefully consider, is x going to be less than 0 or greater than 0? It turns out that when we're going to negative infinity, x is always going to be less than 0. Right? So this is really equal to the limit. Whoops. I didn't leave myself enough room. No. There we go. So we pick up a negative there, right? So we can use this trick. This trick is really just for rational functions, but we can use this version of it as long as we're very careful about, really, as we can see from this, we need to be very careful about it when the variable is going off to negative infinity, right? In that case, we need to think really hard about what all these tricks that we're doing mean. Right? What's happening to x? Why can we cancel these things out? And what do all those pieces, those steps that we are sort of shoving under the rug a little bit look like? Right? So we need to be really careful, but in general, it's the same sort of trick all around. Right? So next section is going to be all about the formal definition of the limit. We did the semi-formal definition a few sections back, but once we get done with that, we're going to start bringing this into derivatives. So I will see y'all then.